Now we're going to take a look at selective reagents, and we've talked about this before. A simple definition that we are going to end up expanding on a little bit is that a selective reagent is one that selectively reacts with one functional group in your molecule in the presence of another functional group without affecting the functional group that you don't want to undergo the reaction. So let's take a look at some examples. The first example is sodium borohydride. We know that it will selectively reduce aldehydes, ketones, and amines, but doesn't reduce most other carbonyl compounds such as carboxylic acids, esters, amides. We could even add nitriles to this list. So in this molecule, we have an aldehyde that sodium borohydride will react with. The ester doesn't cause any problems. Sodium borohydride is selective for the aldehyde. So now, if we do the reduction, we're going to draw the product where sodium borohydride reduces the aldehyde to an alcohol. And the ester, I'm going to leave it alone. I'm not going to change it because this reagent does not touch that functional group. Another case of selectivity is when we have alpha-beta unsaturated carbonyl compounds. So remember that the carbon next to a carbonyl is alpha. Carbon after that would be beta. So this is an alpha-beta unsaturated ketone in this case. So with these substrates, if you use a Grignard reagent or organolithium compound, that reagent could care less about this double bond. It's going to be selective for reacting at the ketone. So here, the ethyl group, we'll just treat it as ethyl minus. That's going to selectively add to the carbonyl. Your double bond, leave it alone, keep it in place. So we've added that new ethyl group. And then, of course, with these types of reactions, we use acid or water to protonate the oxygen. Now, we have the same substrate below, another alpha-beta unsaturated carbonyl, but a different reagent, the organocuprate, that's going to be selective for reaction at the beta carbon of the alpha-beta unsaturated carbonyl. So again, you have to have the alpha-beta unsaturated carbonyl for this reagent to show that selectivity, but if you have it, it's not going to care or react with the ketone. It's going to add to the beta carbon. So the final product we would get in this case, with ethyl cuprate, keep your ketone, don't mess with it. Right, that double bond goes away, and this beta carbon here, that now has the ethyl group from the cuprate attached. So I'll just draw in that new ethyl group. The fourth one that we've seen before is hydrogen gas. It will selectively reduce pi bonds from alkenes, alkynes, and in the carbonyl family, it will reduce aldehydes. We haven't seen this yet, but later on we'll see that H2 can also reduce nitros to amines, but don't worry too much about that one at the moment. But it's not going to reduce other carbonyl compounds. So if we look at this substrate given here, and it's reacted with hydrogen gas. We have an ester. H2 will not reduce an ester unless we use forcing conditions. So just these ambient conditions here, room temperature, low pressure, it's not going to affect the ester. It's not going to affect the ketone. What it will reduce is the alkene. It will also reduce the aldehyde. So in this molecule, it's selective for those two functional groups over the ketone and the ester. When I draw the product, don't mess with the ketone, don't mess with the ester. The alkene gets reduced to an alkane. The aldehyde gets reduced to an alcohol. The last one here is PCC. So we know that PCC is a mild oxidant that can oxidize a primary alcohol to an aldehyde. What that also tells us is that aldehydes are essentially inert to PCC. So with this particular substrate, the only thing that's going to react is the alcohol. So this is a secondary alcohol. With the PCC oxidation, it will get oxidized to a ketone. Let's leave the aldehyde alone. That alcohol becomes a ketone. So again, selectivity is all about the context of the reaction you're looking at, the substrate you have, and what functional groups are present. Will the reagent react with the functional groups you want it to? Will it leave alone the functional groups that you don't want to react? Now let's expand our definition of selectivity just a little bit. So we've been looking at it in the context of two or more functional groups in a molecule. But we can also consider a reagent selective if it reacts at one position in the molecule over another potential position. So, for example, we have alpha carbons that can form enolates when reacted with base. And a base like LDA or sodium methoxide can deprotonate an alpha proton. And just looking at it in this molecule below here, we have alpha protons on this carbon and an alpha proton on this carbon. So a non-selective base could deprotonate here or here. But the bases that we tend to use, like LDA and sodium methoxide, are selective for a particular position. LDA is selective for the less substituted position. Sodium methoxide is selective for the more substituted position. So in this example, we're using LDA, and knowing that LDA is selective for the less substituted alpha carbon, we're going to deprotonate one of these red alpha hydrogen, because that's the less substituted alpha carbon. So there's the selective enolate that forms, and then this one reacts with ethyl chloride. So we can do the SN2 reaction. And that puts an ethyl group there. So that's considered selective because a base could react at either position, but it selectively reacts at one.